You know how it is, you want to quickly get your head around something complex, but without feeling like you need a PhD just to follow along.
Absolutely.
That's really what we're all about here on the Deep Dive. Today, we're taking a pretty fascinating look under the hood, specifically at the security of the Mercedes-Benz MBUX infotainment system.
Yeah, the brain of the dashboard, basically.
Exactly. We've got this detailed research report. It's almost like a treasure map of information, really. And our mission, if you will, is to dig out the most critical, the most, well, interesting finds for you.
Giving you a real sense of the security landscape in these systems.
Right, without getting totally bogged down in, super technical jargon.
And think of it as your express route to getting informed on this specific topic. What's interesting right off the bat, I think, is that this wasn't done in isolation.
Oh.
The research team actually worked directly with Mercedes-Benz on the findings.
Ah, okay. So a collaborative approach. That's good to hear.
Yeah, it shows that, well, a positive attitude towards tackling security in these modern, very complex vehicles.
Yeah. Okay, so where did these security sleuths even begin? It sounds like step one was using the kind of diagnostic software the dealerships use, right?
Pretty much.
Hmm.
Imagine them plugging in and essentially getting this digital blueprint of all the electronic control units, the ECUs, in the car.
Seeing how they're all connected, what they're doing.
Exactly. But what's really key here is how these tools talk to the car. It's not like just plugging in a USB stick.
Yeah.
They use something called DOIP, that's Diagnostics over Internet Protocol.
Diagnostics over IP. So, like using internet tech.
Essentially, yes.
Yes.
Using IP protocols, the same stuff that makes the web work, but specifically tailored for car diagnostics. And it typically happens over an Ethernet connection within the car's network.
Gotcha. And it's not just standard internet chat, is it? There's like a custom language involved.
That's right.
Yeah.
The report mentions this initial communication uses something called CSD. It's an ASCII-based
Yeah,
protocol.
see, so text-based.
Yeah, think of it as a very basic text conversation for the diagnostic tool and the car to, well, introduce themselves, authenticate, set things up for the more detailed stuff.
Kind of the digital, hello, you there?
Yes, I am. Exactly. And after that initial handshake, they switch gears
To what?
to a more complex binary protocol for sending UDS messages, Universal Diagnostic Services.
UDS, okay. And that's where the real action happens.
That's where the diagnostic tools can really get down to business. Checking system health, pulling error codes, and even telling the car to perform specific actions.
And here's where it starts to get interesting from a security angle, right? The researchers figured out how to decode this whole conversation.
They did. They created a special script using LUA to basically translate this relatively obscure car language.
Wow, like cracking a code. And what did they find?
Some pretty powerful stuff. They uncovered UDS commands that could, for example, reset the car's main computer, the ECU,
Okay.
or completely shut off the engine.
Shut off the engine.
While it's running. Potentially, yes. And even things like locking all the doors remotely via diagnostics.
Yikes. That really makes you think about how crucial it is to secure these diagnostic channels.
It absolutely does. And to really understand the potential impact, the researchers had to get a handle on the MBUX architecture itself, how it's all put together.
So what are the main pieces?
The report gives a high-level view. There's the MMB, the multimedia board. It's basically the brains of the infotainment, handles the display, user interaction, all that.
The main computer for the fun stuff.
Pretty much. Then you've got the BB, the baseboard. It handles a lot of the networking communication within the car, connecting to other vehicle systems.
Okay.
There's also the CSD, the country-specific board. This adds features or handles regulations specific to where the car is sold, and it talks to the MMB over a high-speed internal link.
Ah, so customizations for different regions.
Exactly. And finally, they mentioned the RH850 module. Think of that as a gateway or a bridge, connecting the infotainment world to some of the car's more fundamental control networks like CAN bus.
So it's like this whole digital nervous system, all these parts chatting. And how did they test this? Just on computers?
Well, they used both.
Yeah.
They had a real Mercedes B180. Nothing beats testing on the actual hardware.
True.
But they also built their own custom setup, a test bed. This let them isolate specific components, poke around more deeply, without worrying about accidentally bricking a real car.
Smart move. Less risk involved.
Definitely. And one interesting challenge they hit with their test bed was the MBUX anti-theft feature.
Ah, the thing that stops you putting a stolen radio in another car.
Sort of, yeah. In a normal car, right after the MBUX unit starts up, It expects an authentication signal over the car's internal network, the CAN bus,
Mm-hmm.
to prove it's in the right vehicle.
And the test bed couldn't provide that signal perfectly.
Exactly. It couldn't fully mimic that initial "I'm home" signal. So the MBUX unit would often go into this anti-theft lockdown mode, which really limited what the researchers could actually do or see.
Hmm. Okay, so how did they get around that? They didn't just give up, presumably.
No, they're researchers. They took what the report calls an empirical approach,
Meaning?
basically trial and error. They experimented, sending different messages onto the simulated CAN bus, trying to figure out which ones might reset that anti-theft status or trick the system.
Like digital lockpicking, almost.
Kind of. What they found was clever. They noticed certain CAN messages, specifically ones related to the display trying to turn off, would briefly trigger this anti-theft check again.
Ah, a small window of opportunity.
Exactly. And during that split second, the system was more accessible. So they set up this automated loop,
Doing what?
continuously sending that specific CAN message over and over again. It kept the head unit sort of oscillating between being authenticated and triggering the anti-theft check.
So constantly nudging it to keep the door slightly ajar, so to speak.
Precisely. Not the most elegant, maybe, but it worked. It kept the system accessible enough for them to investigate.
Resourceful. Okay, so now they have a stable test environment. What's next? Digging into the software itself.
Exactly. The firmware. The report states that the MMB, that main infotainment brain, runs on Linux.
Okay, Linux. Familiar territory for many researchers.
Right. And all its core files, the operating system, the applications, they're stored on an eMMC chip. That's a type of embedded flash memory.
And getting access wasn't simple.
No. To really analyze these files properly, they actually had to physically desolder and remove the eMMC chip from the circuit board. Chip off forensics, basically.
Wow, that's invasive. Shows real dedication.
It does. But interestingly, they also found another potential source for these MMB files, one that's a bit less hands-on.
Which is?
Turns out these firmware files can often be found on the websites that Mercedes-Benz uses to distribute updates for their official diagnostic tools.
Ah, so if you know where to look online.
You might be able to grab the system files without needing to perform electronic surgery, yeah.
Interesting. And what did these update files look like? Were they straightforward?
They found a few different types, different file extensions. Things like AML, CFF, and SMRF were common.
Okay. Any differences?
Well, the researchers noted that files ending in docbin, which sometimes appear, are often containers, like digital suitcases holding other files. And they might be compressed or have some kind of custom structure.
Right.
Similarly, the SMRF files are also containers, usually compressed and with their own specific format. They often contain encrypted data that the official diagnostic tools need special keys to unlock.
Okay, so protected.
But then the CFF files seem to contain the same core firmware data as the SMRF ones, but crucially, they weren't compressed.
Ah, like getting the raw ingredients instead of the shrink-wrapped package. Easier to analyze, I bet.
Much easier, yeah. So different packaging for essentially the same software update.
Got it. So now they have access to the firmware, the actual code running the system. What did they look at next? How things talk inside the box?
Exactly. They started looking at how the different software services within the MBUX head unit communicate with each other. This led them to investigate the custom IPC protocols.
IPC, interprocess communication.
That's the one. Think of it like how different apps on your phone or different programs on your computer pass messages and data back and forth behind the scenes.
Right, because it's not just one big program doing everything.
Not at all. Inside the head unit, you've got numerous software components, services, all needing to collaborate. They need to talk to different parts of the same program, to other programs entirely, maybe even interface with other ECUs in the car.
And Mercedes uses custom ways for this.
The researchers identified 3 main custom IPC mechanisms being used. One called thriftme, another called MoCCA, and a third called GCF.
thriftme, MoCCA, and GCF. Okay.
And what's really fascinating is that a single service might actually use all 3 of these simultaneously, depending on which other service it needs to talk to.
Wow. Okay. So it's like a multilingual device internally. You really need to understand all these different communication styles to grasp the security picture.
Precisely.
Let's break them down then. Start with thriftme. What's that about?
Okay, so thriftme. The report says it's based on a well-known open-source framework called Apache Thrift.
Ah, Thrift. I've heard of that. Used for building services that can talk across different programming languages.
Exactly. But the me part in thriftme seems to refer to a key addition Mercedes or their supplier made. The ability for services to send out notifications to subscribers.
So Not just request response, but also broadcasting updates.
That's right. Standard Thrift is mostly about making a direct call to a service and getting an answer back. thriftme adds this publish subscribe layer so a service can announce, hey, something important just happened, and any other service that has registered interest gets notified.
Interesting extension. And how does it work under the hood?
The core implementation is in a library file named libthriftme.so.2.7.2. The central orchestrator is a class called thrift.t service broker. Think of it as the main switchboard operator.
Connecting callers and receivers.
Yes. And in this specific MBUX system, they're using a customized version called thrift.lisa.ctlisa service broker.
Lisa, any idea what that stands for?
The report doesn't specify, but it's clearly part of their internal naming. So different software components register their services with this Lisa broker.
And then clients can find them and use them.
Correct. The report mentions base classes like thrift.lisa.tlisa server base for the services offering functionality, and grift.lisa.tlisa client base for the components wanting to use those services.
And it uses callback functions.
Yeah, callbacks are used to handle the actual API calls from clients and also to deliver those notifications we talked about. It seems like a pretty structured, albeit custom, way for services to interact.
Okay, that makes sense for thriftme. What about MoCCA? That sounds less familiar.
MoCCA is another RPC framework remote procedure call. This one was developed by Harman, a big automotive supplier, and it's based on something called the DSI framework.
Harman, right. They do a lot of infotainment stuff.
They do. The main library here is libsys MoCCA framework shared so.10n. And the researchers found MoCCA is used very extensively, especially for communication between different threads within the same process.
So different parts of the same program talking to each other very quickly.
Exactly. The report describes MoCCA's architecture as being component-based.
Components like building blocks.
Sort of, yeah.
Hmm.
Services create instances of these software components using special factory functions. An example given is CHB application builder.the C diagnosis component creator. All these components inherit from a base type called CHB component.
Okay, like Lego bricks fitting together.
That's a good analogy. And there's a central registry, kind of, called CHB component info.spmap. It keeps track of all these component bricks and what they do. It even allows them to have aliases like nicknames, making it easier for other components to find them.
So a directory for the software bricks, how do they actually talk?
MoCCA is heavily event-driven. Instead of one component directly calling a function in another all the time, they often communicate by sending out event signals when something happens.
And other components listen for these events.
Exactly. They subscribe to events they care about and react when they receive them. The report gives an example on the client side. Something called ctrace service client base wants to use a tracing service.
All right.
It does this through a helper object, a proxy, called ctrace service proxy. This proxy tries to be efficient, reusing existing connections if possible. When a response event comes back from the service, an interface called IHB event consumer handles it. It has a main function, process event, that looks at a status code and an internal ID to figure out what the response means and what to do next.
Right. And on the service side, how does it handle requests?
They looked at an example stub class, ctrace service stub. When it receives a request event, its process event function also uses that internal ID from the event to determine which specific function within the service needs to be executed to handle that request. Then it calls that function.
So both thriftme and MoCCA provide these structured but different ways for all the software parts inside the MBUX to coordinate and share data, like internal communication protocols within a company.
Well put. And that brings us to the third one they identified, GCF.
GCF, what's the story there?
This one is described as a fully custom RPC protocol. The key idea here is that services register themselves with a central router.
A router, like a network router.
A similar concept, but purely in software. Instead of services talking directly or just using events like MoCCA, they announce their capabilities to this GCF router.
And then if another service needs something,
it sends a request message to the router specifying which service it wants to talk to and what it wants it to do. The router then forwards that message to the correct destination service.
Interesting. Centralized control, what kind of messages does the router handle?
The report mentions several types. CTRL messages for general control, RGS and REGF for services registering and unregistering, EVNT for broadcasting events, and crucially, THEOL messages for making function requests.
And what does a call message look like?
It's quite specific. It includes the name of the target service, a number identifying the exact function to call within that service, a text name for that function, and then any parameters or data that function needs to do its job.
That centralized router model definitely has security implications. If you can influence the router.
Or if you can impersonate a service to the router, potentially. It's a central point of communication, and often central points can become targets.
Makes sense. Okay, so that covers the software communication inside. Did they look at the physical connections too?
They did. Stepping back from the pure software IPC, they examined the physical links within the head unit hardware itself. Remember the CSB, the country-specific board.
Yeah, the one for regional features.
They found specific test points on the main circuit board that the CSB uses to connect to the MMB, the main multimedia board. This was actually building on earlier research by Keen Lab.
Okay, test points. So places meant for diagnostics or manufacturing.
Presumably. And what the researchers did was quite direct. They disconnected the normal cable linking in the two boards and plugged in a standard Ethernet cable, an RJ45, directly into these test points.
Just jacked right in.
Yep. This gave them direct access to an internal network interface on the MMB, which the system sees as Ether narrow.
And was it wide open?
Not completely. There were some basic firewall rules active on this Ether arrays, restricting access mainly to specific internal IP addresses on the MMB itself, probably intended for internal diagnostics or maybe communication between core components.
But they still got some access.
Oh, yes. Even with those restrictions, the moment they connected, they gained access to a very valuable resource, the DLT subsystem.
DLT, Diagnostic Log and Trace.
That's the one. It's a system commonly used in automotive development for logging detailed information about what the software is doing, tracking events, debugging issues. It's incredibly useful for developers.
And for security researchers, I imagine.
Absolutely. Having access to detailed real-time logs is invaluable. And interestingly, the report notes that this DLT implementation even supported something called callback injection.
Callback injection, what's that?
It suggests a potential mechanism where you could possibly use the DLT system itself to trigger specific functions within the running software, perhaps by manipulating log messages or trace configurations.
Wow, okay, so direct access to logs and potentially a way to interact with the code through the logging system itself. That's quite a foothold.
It really is. This kind of internal network access combined with DLT visibility provides a powerful platform for understanding the system and, crucially, for finding vulnerabilities.
And find them they did. Let's get into the vulnerabilities they uncovered. Where should we start? Maybe with MoCCA. There was one related to that, right?
Yes. CVE 2024-37600. This vulnerability lies within a component called Service Broker, which, as we discussed, is part of that DSI framework used by MoCCA.
The component that monitors other services.
Exactly. It acts like a supervisor, keeping tabs on MoCCA services and clients. And it uses, somewhat surprisingly, internal HTTP servers to manage some of this.
HTTP, like web servers, inside the car system.
For this internal management task, yes. One of the commands the service broker understands is a POST request to a URL ending in disconnect. This is used to signal that a service or client is, well, disconnecting.
Okay, seems straightforward. Where's the vulnerability?
It's in how the code processes the data sent with that disconnect request. Specifically, in a function called setup. This function uses a C function called scanf to parse the incoming data.
Scanf. I know that one. It can be tricky if you're not careful about buffer sizes.
Precisely. The researchers found that scanf was being used in a way that if you sent a very long string of data in the disconnect request, it could write past the end of a designated buffer on the stack.
A classic stack buffer overflow, like trying to pour a gallon of water into a pint glass.
Exactly, it spills over. And when that happens in software, the overflowing data can overwrite other important information on the stack, like return addresses, potentially allowing an attacker to hijack the program's execution flow.
Take control of the service broker process.
Potentially, yes.
Yeah.
Or at the very least, crash it reliably. They even observed crashes related to this showing up in those DLT logs we mentioned.
So just by sending a carefully crafted web-like request internally, you could cause serious problems. Okay, what about GCF? That centralized router system. Any issues there?
Yes. CVE 2023-3440. This involves a service called Monitor Service, which is accessible via the GCF protocol.
Monitor service sounds important.
It gets started automatically when the system boots up by another component called CT, and it reads its configuration from a file. Verops swmpks.config.cfg. This file tells it things like which network port to listen on for GCF messages, monitorservice.port, and whether it should even be enabled, monitorservice.acvalo.
Okay, and what does this monitor service do?
One of the things it does is register a specific function called NWSPF set McAdder exception IP with the GCF router.
Long name. What's its job?
It's responsible for managing firewall rules on the system. It takes arguments like a MoCCA address, a direction in out, a fate, a loud any, and a command, Adderley rule.
So it lets other services dynamically change the firewall settings via GCF.
Correct. The vulnerability lies deep within the code that handles this function. Specifically, in a subroutine the researchers labeled sub F7A F4. This code ultimately constructs and executes a standard Linux command, iptables, to actually implement the requested firewall change.
Ah, it's building a command line string. I sense danger.
You sense correctly.
Correct.
The critical flaw is that the MSC address provided as an argument to the GCF function is not properly validated or sanitized before being directly plugged into that iptables command string, which is then executed via the system call.
Oh, classic command injection. So you could put extra commands in the MSC address field.
Exactly. You could potentially stick shell commands after a legitimate-looking or even fake MSC address, separated by a semicolon or backticks or something similar. When the system call executes the iptables command, it would execute your injected commands as well, with the privileges of the monitor service.
Nasty. That could let an attacker completely rewrite firewall rules, open up ports, or run other malicious commands.
Definitely a serious issue. Now, beyond these flaws in the custom IPC mechanisms, they also found a vulnerability related to privilege escalation, getting more power within the system.
Okay, like going from a regular user to an admin.
Precisely. This one is CVE 2021-40034, and it's actually not a flaw in Mercedes' own code, but in a standard Linux component called Polkit that the MBUX system was using an outdated version of.
Polkit, that handles permissions, right. Deciding which users can do which administrative tasks.
That's it. And CVE 2021-4034, also known as PwnKit, is a well-known vulnerability in Polkit. It's a local privilege escalation flaw.
Meaning you already need some level of access first.
Yes, it allows an unprivileged user who can already run code on the system to trick Polkit into granting them full root administrator privileges.
And there are public exploits available for this.
Oh yeah, readily available. The report mentions that using one of these exploits could allow an attacker to execute commands as the phone user initially, which already has significant privileges.
And from there?
From there, they could potentially manipulate network interfaces, mount file systems, and likely use other system tools, like Systemed, to escalate further, possibly even to full root access.
So a known vulnerability in a common component gave them a potential path to complete system compromise.
It seems so. And adding to the problem, the researchers noted that while the main root file system is mounted read-only by default,
which is good practice, prevents easy modification.
Right, but there was no mechanism found to ensure the integrity of the disk contents, like secure boot or DM verity.
Meaning
An attacker who gains sufficient privileges, perhaps via Polkit, could simply remount the file system with read-write access.
Ah, bypassing the read-only protection.
Exactly. And once it's writable, they can modify critical system files, startup scripts, plant backdoors, anything really.
So combining these vulnerabilities paints a picture of potentially gaining initial access, escalating privileges, and then making persistent changes. That's a significant chain.
It is. So the next logical question is, how would an attacker actually deliver an exploit to trigger these vulnerabilities in the first place?
Yeah, what's the entry point?
The report heavily emphasizes the USB port as a primary physical attack vector.
Makes sense. USB ports are right there on the dashboard, easy to access. Plug something in.
Precisely. And because the head unit uses that microservice architecture, with services talking via thriftme APIs.
The researchers could simulate the USB interactions.
Yes, very effectively. They used QEMU in user mode emulation. This allowed them to run and interact with the head unit's actual compiled code for handling USB devices, but entirely on their analysis computer.
So they didn't need to constantly plug USB sticks into the real car or testbed?
Right, it speeds up testing immensely. The setup involved a few steps. First, setting up the network environment correctly. Then, using a tool called SOCAT to forward the UNIX domain sockets that these services normally use for communication.
Forwarding them to standard TCP network ports on their analysis machine.
Exactly. This allowed their simulation tools to talk to the emulated MBUX services. They then ran their own Python scripts to act as placeholders or partial emulators for key thriftme services involved in USB handling, like device mgr.py, vehicle.py, and varcoding.py.
So they're mimicking the real services.
Partially, yes. Just enough to trigger the code paths they wanted to test in the actual MBUX service they were analyzing under QEMU. And specifically for USB testing, their device mdr.py script simulated the act of mounting a USB file system to a specific path within the emulated environment. Opsys-ban.
Okay, so they built this whole virtual MBUX USB environment. What did they test within it?
One key area was the import and export of user profile data. When you back up your settings, destinations, radio presets, etc., to a USB stick.
Yeah, the My Mercedes backup feature.
That's the one. This whole process is managed internally by the user data service, using its C System Profile Service Simple thriftme interface.
And when you back up, it creates files on the USB drive.
Yes, inside that My Mercedes backup folder. It's a mix of XML files and, more interestingly from a vulnerability perspective, several binary files with the extension .ud2.
Binary files. Always a good place to hunt for bugs. What kind of data is in them?
The report details a few. Commuter route.ud2 apparently contains route data as plain text. Using an ISO 8859 encoding.upreds.ud2, however, is actually in SQLite database file.
SQLite, a full database in there.
Seems so. And the vtab.ud2 and vttuner.ud2 contain proprietary binary data, likely related to voice tags and tuner settings.
Okay. And there's another service involved in notifying when this import-export happens.
Yes, the user data exchange service, also part of the user data component, handles the notifications. The researchers mapped out the whole workflow for both backup export and profile import.
And they wrote scripts to automate testing this.
They did. Trigger restore.py and trigger backup.py to easily simulate these actions in their emulated environment.
Very thorough. Did they look at anything else related to USB data?
Yes, the trace system. Many services support something called HB trace persistence. It allows dynamic configuration of tracing via a file named HBTC on a USB drive.
So you can tell services what information to log just by plugging in a USB?
Potentially, yes. And one crucial detail they uncovered. All these .ud2 backup files are encoded using a proprietary algorithm.
Not standard compression or encryption.
No, handled by a specific class CPU user data encoding handler. But critically, the researchers reverse-engineered this encoding.
They figured it out.
Yes, and they wrote their own Python tool, ud2codec.py, to both decode the official .ud2 files and encode their own modified versions.
That's huge. That means they can craft malicious .ud2 files and feed them to the system.
Precisely. And that ability led directly to finding several vulnerabilities exploitable via USB.
Okay, let's hear about them. What's the first one?
CVE 2024-37601. This is a heap buffer overflow vulnerability that occurs during the decoding process of those .ud2 files we just talked about.
An overflow while decoding, huh?
Okay, it gets a bit technical. The user data service represents the encoded data internally using a string object, CHB string. Part of the decoding involves removing certain special characters. The vulnerability happens with one specific character, hex code 0x7.
Okay.
There's a mismatch. The code that iterates through the string, CHB string.considerator.increment steps, thinks 0x7 is a single byte character based on its value. However, the code responsible for removing characters, CHB string.remove, uses a lookup table, UTF-8 lookup table, which says 0x7 should actually be part of a 3-byte UTF-8 sequence.
Uh-oh. One part thinks it's 1 byte, another thinks it's 3.
Exactly. This discrepancy causes the pointer arithmetic to go wrong during the removal process. It ends up calculating an incorrect length and position, leading to an out-of-bounds memory access. Specifically, it results in a call to memove with a size argument calculated to be mega-1.
Moving mequinum bytes? That sounds bad.
Very bad. It reliably crashes the user data service when it tries to import a crafted .ud2 file containing this problematic sequence.
And crashing that service takes down the whole infotainment system.
Yes, the report states it freezes the system completely, requiring a hard reset of the ECU to recover. So just plugging in a malicious USB could effectively brick the infotainment unit until it's rebooted.
Nasty denial of service. What else did they find via USB?
CVE 2023-34402. This one involves that vtab.ud2 file. Remember, it gets decoded into an XML file, vtab.xml, and processed by the text-to-speech service.
Right, the voice tag file.
What they discovered is that this vtab.xml file can contain instructions embedded within the XML structure, telling the system to drop or write another file onto the file system during processing. This happens in a function called user-data-exchange-service-client.unpack voice-to-archive optimized.
Okay, so the XML can tell it to create a file. Is that validated?
That's the vulnerability. There are apparently no checks on the path where this new file is supposed to be written.
Oh, wow. So the attacker controls the file name, the location, and the content.
Yes, By crafting a malicious vtab.xml inside a .ud2 file, an attacker could write arbitrary data to potentially any location on the file system that the user data or text-to-speech service has write permissions for.
That's an arbitrary file write vulnerability. Huge potential for planting malware or overwriting critical files.
A very significant finding, yes. And there's one more major USB vulnerability, CVE 2023-34399.
Okay, what's this one?
This involves the opreds.ud2 file, the one that decodes into an Skylight database, opreds.db.
The database used by the machine learning routing service.
That's the one. The database gets imported, processed through functions like capthrift.capserver.request binary data and capthrift.capserver.setProfile. Now, the way the data within the Skylight tables is handled internally involves serializing it using the Boost library's serialization framework.
Boost, a popular C++ library.
Very popular. In this case, it was configured to use plain text serialization. The vulnerability is an integer overflow within the Boost library itself. Version 1.81 was the latest at the time of research, when it processes entity pointers during deserialization.
An integer overflow in Boost. How does that get triggered?
It happens when handling a specific value from the database called SID. An attacker can control this SID value by crafting the opreds.db file. The SID value is used as an index into an internal array, conjected vector.
Okay, using attacker data as an array index. Usually dangerous.
Very. While there are some checks on the SID value, the researchers found a way to bypass them by setting SID to miniker 3. This negative value, due to the integer overflow during processing, corrupts another crucial internal pointer called bspr.
Corrupting a pointer, that can lead to crashes or worse.
Exactly. The report includes GDB debugger output showing the bspr getting corrupted and the subsequent segmentation fault when the program tries to use it.
So they can crash the service reliably. Can they exploit it for code execution?
They believe so, using a technique called heap spraying.
Heap spraying, filling the memory with predictable data.
Right. Because they control the contents of the Skylight database, opreds.db, they can fill it with carefully crafted data. Specifically, they created many tables with very long names, DDL entries. This floods the program's heap memory in a somewhat predictable way.
Why?
The goal is to control what that corrupted bspr points to after the overflow. If they can make it point to attacker-controlled data, part of their heap spray, they might be able to hijack the program's control flow when it tries to use that pointer.
Taking control of the keep server service.
That's the aim. They even provide an example of the malicious Skylight structure and mention a script they wrote to automate generating these databases, potentially varying the spray pattern based on time to help defeat memory layout randomization, ASLR.
And does the service just die, or does it restart?
Crucially, the report notes that the CAPE server service is configured by Systemd to automatically restart if it crashes.
Ah, that's perfect for exploitation. If the first attempt fails, it restarts. Maybe the memory layout changes slightly, and they can try again. Allows for brute forcing.
Precisely. It makes exploiting the vulnerability much more feasible, even with memory protections like ASLR in place.
Wow. So multiple serious vulnerabilities, denial of service, arbitrary file write, and potential remote code execution, all triggerable just by inserting a crafted USB drive.
That's the conclusion, yes.
Yeah.
The research successfully compromised their testbed environment using these methods, and the vulnerabilities were confirmed to be present in the software intended for real vehicles.
And what did they suggest these exploits could be used for in the real world?
They listed 3 main potential use cases. First, disabling the anti-theft mechanism on stolen MBUX units to allow them to be reused or sold.
Okay, facilitating theft.
Second, potentially tuning the vehicle or unlocking paid features or services without authorization changing variant coding, for example.
Performance tuning or getting features for free.
And third, simply as a foothold for further security research, allowing deeper access to explore other parts of the vehicle's systems.
Right, a starting point for more digging. Did they list all the CVEs found?
They did. It's quite a list. Reflects the depth of the work. Let me see. CVE 2024-37602, CVE 2024-37601, CVE 2024-37601, CVE 2024-37601, the UD2 decode overflow, CVE 2023-34406, CVE 2023-34401, CVE 2023-34397, CVE 2023-34402, the XML arbitrary file write, CVE 2023-34403, and CVE 2023-3404, the GCF command injection.
That's a dozen vulnerabilities. Quite the haul.
It is. And they mentioned that the full details for each CVE would be published on their linked GitHub repository for others to review.
Good. Transparency is key.
They also included relevant keywords summarizing the research areas: automotive security, CAN bus, diagnostics, privilege escalation, USB attacks. It really covers a lot of ground.
Okay, so to kind of wrap up our deep dive today, it's clear the researchers did an incredibly thorough job dissecting this MBUX system.
Absolutely. From the initial diagnostic protocols right down to the nitty-gritty of internal communication frameworks like MoCCA and GCF, and especially the USB attack surface.
And they found significant weaknesses across the board: buffer overflows, command injection, ways to write arbitrary files, even leveraging a known OS vulnerability for privilege escalation.
It really paints a picture of the complexity inherent in these modern infotainment systems. They're powerful computers, running complex software stacks, and with that complexity comes a large attack surface.
And the potential impact isn't trivial, right? We're talking about system instability, unauthorized access, potentially modifying car features.
Definitely serious considerations, especially as these systems manage more and more vehicle functions and personal data.
But it's also important, as you said at the start, to highlight the collaboration here. The researchers worked with Mercedes-Benz on disclosure.
Yes, that proactive engagement is crucial. It allows the manufacturer to understand the issues and develop fixes, ultimately making the vehicle safer. It's the responsible way to handle vulnerability discovery.
Absolutely. So it leaves us with a final thought, perhaps. As our cars become essentially computers on wheels, packed with connectivity and features,
Hmm.
what are the broader implications? How do we, as users and as an industry, balance all this amazing convenience and connectivity with the fundamental need for security and privacy? Where's that line?
That's the million-dollar question, isn't it? It's an ongoing challenge, constantly weighing the benefits of new tech against the potential risks. Definitely something to keep thinking about long after this deep dive ends.